Hey, today we're going to talk about 7.7, acid rain. So take a moment, check out the enduring understanding, look at the learning objectives, pause the video, review the essential knowledge, and set up your Cornell notes. Okay, so the title of this is Acid Rain. This is kind of interesting. Why the College Board did this, I don't know. Everything over here, the learning objective says acid deposition, acid deposition, acid deposition. So acid rain is acid falling in water or acidified water that is falling down to the earth in liquid form. Acid precipitation implies that it could be rain, sleet, snow, etc. And acid deposition implies that it is something falling not in liquid or water form. So it could be anything else that has been acidified, like little flakes of acidified substances that are falling back or coming down to the earth. Okay, so if we use acid rain, acid deposition, acid precipitation, it doesn't really matter. They all kind of fall under the same umbrella. It's just different ones are more inclusive. So remember that this is a review, hopefully from chemistry, but the pH scale is a logarithmic scale, and it measures the concentration of H plus ions in molar or moles per liter. So this is the molarity, capital M, and H plus ions is also known as hydronium, and that's when it's H plus water. So it's the aqueous version. Now, when something has a pH of 0, it has 10 to the 0. In other words, 100% H plus concentration, or a molarity of 1.0. And when you have something that is a pH of 1, it has a molarity of 10 to the minus 1, or a molarity of 0.1. And 0.1 moles per liter, 0.01 moles per liter, 0.001. So as you go on, and this is 0.000000014, places. Now these are considered acids, these are considered bases or alkaline, and pH of less than, typically something to be acidic would be a pH of less than 6-ish. Neutral is considered between 6 and 8. And it doesn't mean it exactly has to be 7, and if it's 7.2, that means it's basic. It doesn't mean that. So roughly 6 to 8 is going to be the neutral zone. Now, battery acid would be an example of something with a pH of 0. Lemons have a pH of 2. Bananas, pH of 5. Baking soda, pH of 9. Now, these are bases. Ammonia, cleaning solution, it has a very pungent smell. Ammonia, pH of 11, and bleach, pH of 13. Now, how many times more H plus ions are present in a sample of lemons than in a sample of bananas? So what you do if you get a question like this, you're going to look and you basically make two little notches, and you start with pH 5. And when I'm going this way, I have more H plus. When I go this way, I have less H plus. So if I'm starting at 5, I will move, that is 10 times, that is 100 times, that is 1,000 times more H plus ions in a sample of lemons than in a sample of bananas. Okay, how does this occur? So this map represents areas where you have acid precipitation in the country. So if you look here, we have Chicago, Detroit, and Cleveland. All three are very industrial cities. They're very known for being very industrial, and historically they're located near the Great Lakes or on the Great Lakes. So there's an amazing shipping source back when the Industrial Revolution was occurring. But where you have these sources of acid precipitation, or where you have major manufacturing where you're releasing a lot of air pollutants, the acid rain doesn't actually happen in the same exact location. So let me show you. So some of the contributors to acid rain are the combustion of fossil fuels. That's the major contributor. Coal, remember, has sulfur dioxide and nitrogen oxides. Car exhaust is going to typically have NOx. So we are releasing sulfur dioxide, we're releasing NOx, nitrogen dioxide, and it's a gas. It's going to float up into the atmosphere. Then it mixes with water. So we're getting a little bit now. Now it's dissolving in the water, and it will eventually travel tens, hundreds. I don't think it might travel 1,000 miles, but it could travel, a few hundred miles. And then what happens is it has formed, in this reaction with water, this is sulfuric acid, this is nitric acid. Both of these have very low pHs. So eventually they will fall back down to the earth as rain. However, it's going to be acidified rain. Ew, look at that, acid rain. And then it's going to land on plants, and the vegetation will be destroyed because the acid can damage the tissues, but also it can impact the soil. And I'll go over that in a moment as well. So acid precipitation, again, the big takeaway, it does not occur. It will not happen in the same spot where it was created. And also, since it's a secondary pollutant, it's going to take a little bit of time for that to form. Just like it takes a little bit of time for the tropospheric ozone to form, which was a secondary pollutant, acid precipitation is also a secondary pollutant. So the effects of acid rain are acidification of biologic tissues and of the soil, which I will describe in a moment. And also you can have corrosion of limestone or marble structures. A lot of the buildings in ancient Greece are being destroyed and eventually are being corroded because of the low levels of acid rain. All rain is slightly acidic, but acid rain has a much lower pH, which means it will break down these limestone structures much more rapidly. Also, it has a problem especially for organisms with a narrow range of tolerance. This could be, for example, the pH. Maybe it's the pH between 6.0 and 8.0. Now, another organism might come in and be between 6.5 and 7.5. That means that the pH, if it gets adjusted slightly, some organisms will be living in or won't be able to survive outside of their range of tolerance. And I have a picture of a frog here because amphibians are very prone to the effects of acid rain because they live in the water, and they actually have they have really porous skin, so they breathe through their skin, and any water, any acid that touches their skin is going to go internally, and it is going to definitely impact their chances of survival. So the frogs, amphibians in general, are very susceptible. So if you see a huge population decline of frog population, chances are it could be affected by some form of pollutant, possibly acid precipitation. Now, the soil acidification is a major problem. And remember the particles that make up the soil. We have clay, we have silt, we have sand. Well, clay particles are negatively charged. And they are typically best in pHs that are neutral. Now what happens is all of these positive ions, these cations, are attracted to the clay particles. Because again, the clay particle is negative, and these ions are positively charged. So they're going to be more attracted to the clay than they will to water. Now what happens when you lower the pH? Well, when you lower the pH, you're actually increasing the amount of H+. Now this H+ is kind of a little pushy. It goes in near the clay particle. Remember, the H+ is attracted to the positive charge of the hydrogen is attracted to the negative charge of the clay. And these little H's, they're small. They can get in there and push in, and they can push in and basically shove out these positive cations. Now, a positive cation like aluminum is actually not, plants don't want it. It's toxic to the plants. So if you have aluminum in your soil, the aluminum is better held by the clay particles, and holding it into the clay means that it will not run off and enter plants. But once you have acidified soil, the clay particles are not as able to hold on to some of these toxic heavy metals like aluminum, like cadmium, like chromium. And what happens is they can be easily picked up by plants because this aluminum is now in the water and it's not attracted to the clay particle, it's now attracted to the water molecule. It can be picked up by the plants. And eventually can lead to their death, or the plants being outside of the range of tolerance. Now, what happens to other nutrients, like, for example, nutrients that plants need, like calcium, like sodium, like potassium? Well, these H+, when you have acidified soil, the H+ can do the same exact thing. It can push these cations, these beneficial nutrients, it can push them out of the clay particle, which means it is found in the water, which can easily run off and enter a larger body of water where it can contribute to eutrophication. So soil acidification is a problem because nutrients are not able to be held strongly by the soil or the clay particles, which are negatively charged. So how do we remediate this? How do we fix the problem once it's already happened? So let's just say I have a pH, a soil with the pH sample like between 4 and 4.5. Now that's way too acidic. One of the things that I could do is add calcium carbonate. And calcium carbonate, another way, it's limestone, but in a lot of the texts and a lot of the College Board questions, multiple choice, what have you, it will be called lime. It doesn't mean you're adding lime juice, because lime juice is acidic. We're adding lime. When you're adding it, it's basically this white powder, and it is bringing the pH back up to a more neutral pH level. So there was a lot of information. I want you to practice, and this is like a research project. So this FRQ practice, researchers want to explore the impact of acid deposition on the survival of isopods, these guys, in the soil of deciduous forests. During the exploration, rainwater with different pH values is collected and misted onto pots of soil taken from a temperate forest. During the experiment, the scientists record the number of living and dead crustaceans found in each pot of soil. So you're going to do three things. First, identify a likely hypothesis for this experiment. Second, identify the independent variable for this experiment. And third, explain how the results of this experiment would change if crushed limestone were added to each soil pot. Thank you so much for your attention. I hope that this was informative. I look forward to seeing your responses to this FRQ practice, and I will see you soon.